Hello, today is our last lecture on work and energy. I will be solving an exercise that combines almost all the formulas that we learned in this lesson. So we will encounter work function, kinetic energy equation, potential energy, mechanical energy conservation, work energy theorem, almost everything. So let's do it. The adjacent figure represents the motion of a sphere of mass m equals 70 kilograms. So we have the mass along the path A, B, C. Okay. The path AB is frictionless. So they are telling me that the path AB is frictionless. If it's frictionless, implies I can apply mechanical energy conservation on the path A. The path BC is rough and the coefficient, sorry, and the coefficient of kinetic friction is 0.2. So here I cannot apply conservation of mechanical energy, but here I can apply work energy theory. Take G to be 10 and GPE equals 0 along BC. So over here is our reference where G E is equal to 0. Okay. The sphere starts from point A with a speed VA equal 5 meters per second. So VA is equal 5 meters per second. Calculate the mechanical energy at point A. So the sphere has a speed, implies he has kinetic energy, which is half mA squared. He's also at an altitude h, implies he has QPE, which is mgh. So mechanical energy at A is equal to half mA squared plus mgh. So this is mechanical energy at A. So part A, let's start. A. Mechanical energy at A is equal half m, which is 70, times v squared, which is 5 squared, okay, plus m, which is 70, times g, times h, which is 1.5. And this will give me, by the calculator, using the calculator, 1925. So this is mechanical energy at A. Use the conservation of energy between A and B to show that the speed at B is VB equals 7.4. So at B, what is happening? At B, this skier is coming down, 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 down. He's speeding up, 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 up until he reaches point B, right? So he has VB. So at B, there is VB, implies there is kinetic energy, which is half mVB squared. There is no H, it's at the reference of GPE, so that's mechanical. So mechanical energy is just the kinetic energy. So we will come here and we will say, so let me write it here, mechanical energy at B is just the kinetic energy. So part B, mechanical energy at B is equal to kinetic energy at B, which is half m squared. Instead of m, I will directly put its value, 70, times VB squared is equal to mechanical energy at A, which is 1925 joules. Okay. Now, okay, so what will I get? 70 over 2 is 35. VB squared is equal to 1925. So VB squared squared is equal 195 divided by 45. BB squared equal 5 plus VB is equal to square root of 55. This gives me 7.4 meter per second. So exactly the number given here. Okay, so we prove. Part B. So what's happening at B? Okay, let's do it here. Let's change the color just to see the difference. So part B, part A. Now, between B and C, the force of kinetic friction slows down the motion of the sphere and brings you to a full stop at C. So what's happening here at C? How much is V at C? V at C is equal to 0, right? And if V at C is equal to 0, implies kinetic energy at C equal to 0, right? Okay, so friction makes the sphere stops. Find the magnitude of force of friction. This is the first part. So we need to find friction. Friction, the formula of it is mu times m, right? Mu, it's given 0.2 times m. Now, how to find the normal force? We agreed every time they ask me about the normal force, I have to use Newton's second law, which is summation of Fy is equal to 0. Okay, so now I come here. He has already drawn for me the free body diagram. I have n along the y-axis, I have weight along the y-axis, and I have friction along the x-axis. So what do I have along the y-axis? What do I have along? Let's draw the vectors. See them clearly. So this is my y-axis and this is my x-axis, right? So what do I have along the y-axis? I have n and w. So I have n minus w is equal to 0, which gives me n equal w, which gives me n equal m times g, which is m is 70 times 10, which is 700. So I got that normal. Now I go back, F is equal F is equal 0.2 times normal. So it is 0.2 times 700, and this gives me 140. This gives me 140. This is a force, so it is Newton. So this is the first part. Find the magnitude of friction and express the work done by friction on the sphere between B and C in terms of the distance. Okay, so here I have to remember that the work by any force, in this case by the work of friction, is equal to Fx delta x, right? Now, what is Fx? X is in this direction, the x-axis is to the right, and F is in the opposite direction. So this is minus F times delta x from B to C. Okay, and this is equal. I know now that my F is 140, so this is minus 140 times delta x from B to C. Okay, okay, finally, part B, using the theorem, delta mechanical energy from B to C equal work done by friction. So this is our work energy theorem, okay? Find the distance BC traveled by the sphere before coming to a full stop. Now, what is delta mechanical energy from B to C? remember, mechanical energy is nothing but mechanical energy from B delta mechanical energy from B to C equal delta kinetic energy from B to C plus gravitational potential energy from B to C. If there is a spring, there will also be B plus EPE from B to C. Okay, but we don't have a spring. So this is the formula delta mechanical energy. Now let's look from B to C. Is there change in height? Is there any change in height from B to C? No. So do we have delta? So do we have delta GPE? Sorry, here we have to add. Let me do it quickly. So the edge of the height of the skier between B and C does not change. So there is no delta GPE between B and C. So this one here is cancelled. There is no delta GPE. Okay, so we are left with delta kinetic energy between B and C. This is equal to work done by friction. So we have delta kinetic energy between B and C is equal to work done by friction. Delta kinetic energy between B and C is kinetic energy at B minus kinetic energy at C. This is equal work done by friction, which is minus 140. The distance between B and C, so delta X between B and C. Now, what is kinetic energy at B? It's half mvd squared minus kinetic energy at C, which is 0 because it stops completely. Sorry, here the delta is kinetic energy at C minus kinetic energy at B. Okay, because it's delta, so it's final minus initial. So it is 0 minus half mv squared vd squared. This is equal minus 140 delta x. Okay, so let's plug minus half times m is 70, right, times vb squared, it is 7.4 squared. This is equal minus 140 delta x. Okay, just using the calculator, we will get delta x to be the minus will cancel the minus. So let me do the math for you here. Let's do the math here. Okay, so let's do it here. What will we get? So we have minus half times 70 times 7.4 squared. Using the calculator, minus half, so minus 0.5 times 70 times 7.4 squared. This is equal minus 1916.6 equal minus 140 delta x. So we get delta x equal minus 1916.6 divided by 1 divided by minus 140. The minus cancels the minus. So divided by 140, and we get delta x equal 13.7 meters. So this is here just a continuation of it. So in this question, we revise kinetic energy, GPE, conservation of mechanical energy. It happens because there is no friction between A and B. Then we revise work energy theorem. We revise how to get the work of a force. So the work of a force is Fx delta x, right? We remembered how to solve for F. We use summation of y equal to 0. So we revise most of the ideas in this chapter. Tomorrow we will start with a new chapter, which is not on mechanics. So we will move to a completely new idea. So that's it for today, and have a good rest of the day. Bye bye.